morning was happy. I think this class, and I have not changed. I've basically each semester, all I do to make a new exam is I make a few changes, but it's the same basic exam that I gave last semester. And I got to say that this semester has been one of the happiest of my career here in terms of statistics exams. I have not been angry when I've been, and my wife can attest that sometimes when I'm grading tests, I'm like, why? Why can't they form a sentence? So thank you for that. I really appreciate it. Okay, so do I have all of the tests back who are getting them? These two, that person, good. Okay, so we do need to move on. We're moving on to this new topic. So up until now, we've had the t distribution and the z distribution, the normal distribution. Those were the only two. So this is a new distribution, the chi-squared distribution. And I know you're going to look at this and you're going to say, chi, whatever. Just know that when I say it, I'm going to say it right. Remember that chi rhymes with I and sounds like sky without the S. So if you remember that, that might help. I don't know. But this is the chi-squared distribution. It looks like an X, like a cursive X, but that's a Greek letter. So just so you know, when I say it, you'll know what I'm talking about. And we'll just go on from there. So this distribution is useful in a bunch of different statistical settings. We don't need to go into the details of how we compute this, at least not the gory details of it. Let's see, where is this? So chi-squared, it comes in three major flavors. We're only going to take a look at two of them, but I'll show you all three of them. The first flavor, the first version, I know, just like M&Ms come in different flavors. But the first version is the goodness of fit test. We're doing that today. So this is today. We'll do the test for independence on Friday. And then the test for homogeneity, we'll skip because I skipped on Monday. It's not a big deal though, because the homogeneity test is almost the same as the test for independence. They're very similar. It feels almost like the same thing. So we'll just not worry about it. And if you have some sort of advanced research methods class, then you might have to deal with it, but who cares? At least not now, you probably don't care. So here's the deal with this chi-squared distribution. It has degrees of freedom. That feels familiar, doesn't it? You have this, when you're doing the t distribution, you had a degrees of freedom, and the degrees of freedom were the number of things in your sample minus one. Now, degrees of freedom, one way to look at this, well, I'll show you actually, it was kind of hard to understand what degrees of freedom meant back in that setting, but here, it's really easy. I'll show you exactly what it means. But for now, I should say that, sorry, that you don't have to write this down. This is just the mathematical background that I feel like I have to say. And that is that this chi-squared distribution, interestingly, the average of the chi-squared distribution is the degrees of freedom. The standard deviation is the square root of 2 times the degrees of freedom, whatever that is. We'll find out in a minute. It's non-symmetric. It's skewed to the right. Starts at 0. It goes all the way infinitely to the right. The mean is located just to the right of the peak, and the total area is 1. So there's a bunch of properties of the chi-squared distribution. And as you increase the degrees of freedom, the curves become more normal. This sort of feels familiar to us in terms of the t distribution being similar. So here's a couple of examples of the chi-squared distribution. Once again, I'll let you know when you care. This is more just, I'm contractually obligated as a mathematician to actually share some of this with you. But it's kind of interesting. If you have 2 degrees of freedom, you have this very, very skewed distribution. That's what it would look like. Degrees of freedom, if it's 24, you end up with more of it looks more normal, doesn't it? And the higher the degrees of freedom, the more normal it's going to look. But generally, we're not going to be dealing with 24 degrees of freedom. Usually it's going to be 3 or 4. You'll see why in a bit. So you're going to have to deal with tables. This is kind of an unfortunate, I guess, fact of the fact that we're using Newton. I would personally prefer not to use the tables because we have Excel, but because of the way that Newton is set up, we're going to use the tables. So let me explain what the table does for you. So on Newton, whenever you do a problem, it will give you a table like this, and it will say, you're supposed to use the table to make your conclusions. So instead of computing a p-value, what Newton, or what using a table means is that you've got the cutoff. These are kind of got like cutoffs for how extreme you can be and still accept or not reject the null hypothesis. So how bad can things be and still not reject the null hypothesis? This is similar to if you were to do this with a normal distribution, just to relate to something you're familiar with. Let's say that your alpha was equal to 0.05. Then it turns out that with a normal distribution, this is going to be 1.96. And you put a negative 1.96 down here. There's 95% here. So what the cutoff, what this critical, this number that we're about to look up in the table means is it's kind of like where you would put the marks on a normal distribution if we were doing a normal distribution to say that this is going to be 95% in here and this is the extreme stuff. So you can sort of see where this is going, that if your test statistic ends up out here somewhere, then your p-value is going to be lower than 5%. And if your test statistic is in here, your p-value will be greater than 5%. So this gives you a cutoff as to where you're going to reject or not reject the null hypothesis. So here you reject the null hypothesis out here if your test statistic is like there, and in here you fail to reject. So you're going to have the same sort of thing on this picture. Where is it? There it is. On this picture. So what this table does is it just gives you the cutoff. You're going to reject the null hypothesis over here. You're going to fail to reject the null hypothesis over here. And what we're going to do momentarily is we're going to compute the chi-squared and determine whether you fail to reject or reject the null hypothesis. So let's just explain the table though. So I'll have to explain degrees of freedom in a minute. But for now, let's just trust me that you can do, degrees of freedom are easy to compute. You're going to compute your degrees of freedom. I'm going to check my levels. I'm a little hot. I just realized I hadn't checked to see if the mic was working. It is. So you're going to compute your degrees of freedom. Trust me, it's easy. And then you're going to look up in your table this value. And what this value refers to is it refers to the chi-squared cutoff when alpha, when alpha is this little number down here. So this first one, I'm asking you for degrees of freedom 7 and chi-squared of 0.005 or 0.05, that's an alpha level of 0.05. And you can just do this and find where those intersect. There it is. That's the number. That is that particular cutoff. In other words, if when I get done, if my degrees of freedom were 7, if when I get done computing for these M&Ms, the chi-squared value, if it's bigger than this, that means I'm over here somewhere and I reject the null hypothesis. If my chi-squared value is less than this, then, which it's probably going to be honest, I just got to warn you, then I will fail to reject the null hypothesis because I'll be in this big bulge here. So that's what this does. So see if you can do the second one. Figure out where chi-squared of degrees of freedom 6, and I want the alpha level to be 0.005. And meanwhile, I'm going to grab attendance. So I haven't done that yet. So give me a sec. Oh, no, I'll do this later because I can do it while you're doing your M&Ms. Okay, so you've got yours. I know it's so easy. So let's find it. Here's this 6. So I go over to there, and that's the number. So it's 18.548. So that would be the cutoff. Reject the null hypothesis if you're more extreme than this. Fail to reject the null hypothesis if you're less than extreme. So this is like a cutoff. It's the dividing line between rejecting and failing to reject the null hypothesis. Okay, so now the goodness of fit test. What this does for us is it allows us to test statements like this. And I know this is kind of generic, so I need to get a good example. A good example would be these M&Ms, which I'll explain in a minute. So the population fits the given distribution, or the population does not fit the given distribution. Notice that the null hypothesis, similar to the null hypothesis so far, is always in equals. Even though this is in words, what this conveys to you is that there is something equal here. It fits. something fits. Now you might wonder, what do we mean by the population and it fits? So when we get to the M&Ms, what we'll do is we'll actually write this. In fact, we might as well do it now, is I went and in preparation this weekend, I knew we were doing this. I went to get M&Ms and I found that they were having these on sale. And I was like, hey, I'll get the cute Easter pastel colors because I've never done this with the pastel colors. So we'll see if this works or not. But you'll notice on the picture here that each one of them, that they have 5 colors. And so the thing that I want to see is whether or not the colors are all equally represented. Like, do you have just as many pink as you do baby blue and green? Like, are they all the same, percentages, or are they different? So the way I would write this, let's see, do I actually have this? Just a minute. This is, the PowerPoint is not working for me right now. I'm going to have to restart. Here we go. No classes, homogeneity. I don't have it. I'll have to write it out. It's okay. No, not that. There, goodness of it. Goodness of it. We'll do independence on Friday. Okay, so let's actually write this down and there's that formula at the bottom. Don't worry, the formula is easier than it looks. So with the M&Ms, here's what I'm going to say is to say this in terms of the M&Ms, usually what you're referring to is some sort of either a published distribution or something. Actually, I do have, hold on a minute. Here we go. So this is what M&M Mars claims the distribution of M&Ms, plain M&Ms are. So if you're a M&M connoisseur, you know that M&Ms are not equally distributed. And so this is on the website, this is what M&M Mars claims. They claim that brown is 13% of all M&Ms, yellow is 14. These are not the pastel ones. So that's why I'm excited to try this. So this is the distribution for M&Ms. So you notice the null hypothesis is basically saying that this is the correct distribution. So getting back to these M&Ms, because these are not the normal M&Ms, here's the wait, not that. Keep going to the wrong slide. Okay, so here's the null hypothesis that I'm going to be testing. Is I want to know let's see, get rid of that because I don't like it. Okay, so the null hypothesis is Easter M&Ms colors are equally distributed. And I'll just put in parentheses, what I mean by that is 20% each. You'll notice that on this, there are 5 colors, 20% each, right? So that's what I want to test. That's the null hypothesis. That's what I mean by this. So you're going to have to actually think about how you word that. It's not going to be symbols, sadly. It's going to be just as bad for me as it is for you because I have to read your words. But anyway, getting back to this, the alternative is that colors are not equally distributed. So this is what I suspect, just because M&M Mars confesses on their website that regular M&Ms are not equally distributed. Like there's more of, I forget what color is the most popular, yellow or something. I think it depends on if you're peanut or plain. So the distribution is not equal in regular. So I think this is my claim, is that the colors are not equally distributed. Okay, so what's this? Well, this is the calculation that we're about to do. And I'll walk you through it. It's not that hard. I know it looks scary, but it's not that hard. So what does this mean? This is the expected number, the number we expect. So what we mean by expect is if the null hypothesis were true, then I would expect to have a certain number of each color, 1/5. That is the observed number. You'll see me use this in just a minute. We're going to take that and square it and divide by the expected number. And then this symbol, which I know it looks scary, but it's not bad. It just means add them up. So this is add them up. That's what the big sigma means. So we're going to add up a bunch of things, and they're things that we can easily compute. This is easy. I know you're looking at it thinking it's scary. Oh, and I guess we need to get back and talk about degrees of freedom eventually, but let's do the M&Ms first. So what I would suggest you do, so I have this, I'll give you this just a sec. So I printed this up for you. You find it, so you don't have to copy that down. Here it is. Okay, so here, I'll do this in two ways. So first of all, I've got these for you. So these are just that there, what you see up there. Why is that? Don't scan yet. I don't know why it's not showing up. But anyway, I'll fix that in a minute. So this is just a table to help you compute what we're doing here. So I'll show you how to do this. Let me just pass this around, and then I'll pass around, or here, we can pass around the M&Ms as well. There are both plain and peanut, and there are enough that almost everyone can have what they want. So if you're in the back, sorry, oh, I should go to the back first because I was going to collect the back. Here, I'll give a few to the front, a few to the back, and then the middle people will be discouraged. Sorry. Here, you can pass the extras back. Let me go to the back here. Take what you want and then pass the rest forward. So there's plain and peanut. Here's a few here. Yeah, don't open them up yet. I put them in plastic clear so that you could do this without eating any. I know you want to eat them, but not yet. Let me pass this around, and then I'll explain what to do here. So you can hopefully figure out which one's plain and which one's peanut by the shape of the M&M. If you're not familiar with the fatter ones, I'll take that one. Here, you can pass these around. There's a couple. You have extras, excellent. You don't want to, you wanted one for your brother? Well, if there are any left over, well, there will be. There's lots of extras. Oh, it's because we have absent people. So the people watching the video are going to feel sad. Wow, so many extras. My calculus students will be happy here. Okay, who's got extra? You didn't get one. You have extra. I was not careful with my distribution of these pages. You have an extra one, thank you. Okay, I just need, anyone else need? So we have the papers, and does everyone have a paper? Okay, and then we have the M&Ms. Does everyone have the M&M flavor that they want? Because I have extras here that I keep dropping. The extras will be available in the math offices later today. If you get hungry, just stop by. Okay, so here's what I'm going to do just to show you how this works. Let me do plain, because plain is more fun in my mind. Just want to show you, and then this also will help the people who aren't here feel bad that they aren't here. Give me a sec. I think I have to do this. Okay, just a minute. Yeah, I think it's pretty obvious, isn't it, what we're doing? But just in case, you're going to count the number of each color, which I'm about to do if I could get this to work. Camera unavailable. Just a minute. I have to take a photo of my M&Ms here. Here we go. Let's see. There, I think I can see them all. Okay, so I'll put this in the slides. Yeah, but yeah, you're going to count, and then you're going to basically add. Yeah, we'll talk about that in a minute. So there's that done. Good enough. Where's my thing there? There we go. Okay. Okay, so give me a minute. I will do my count. You do your count. You're going to fill in. If you're not sure what to do, you can watch what I do in just a sec. So pink is 3. Yellow. You're probably already done. Oh, sorry. Don't do that yet. Oh, come on. Okay. Blue. Green. 6. Purple. Wow, my distribution doesn't seem to be even. Okay, so let's see. 3, 8. I know what I can do. Let me just copy this, and then I'll explain how we're going to compute this. So it may be self-explanatory. Some of you are probably doing the calculation. That's fine. 3, 8. Okay, there we go. Okay, so when you get done counting, you should have something like this. Oh, you should also mark down that, is it plain or is it peanut? And as you probably guessed, I actually measured these at home using my food scale so that everyone got one serving, which is about 28 grams. I actually was a little bit liberal with you, and I gave you between 30 and 32 grams. So, but because peanut M&Ms are so big, you might even, like this bag doesn't even have any purple, interesting, or lavender. So you might, you have fewer is what I'm saying. That's why I like the plain better in terms of this. Okay, once you have this, what we're gonna do is we're gonna compute the total, and everyone is gonna have their own total. So don't feel like yours should be the same as mine. So basically you're adding these up, 3 plus 8 plus 1 plus 18 plus 6. Give me a minute. I believe I got that right. So you'll have your own total. I've got 36. Next, you're going to want to whip out a calculator because you're going to have to compute the expected number. Now, the expected number, this number, it says FE. That just means frequency that we expect. That's the frequency we would expect if the M&Ms were equally distributed among all the colors. You see, you might say, well, but they're clearly not. I only got one blue M&M. Yeah, but you have to realize what happened is I had this bag. I actually had 2 of these bags at home, and I'm dumping, and in the bag, there might have been an equal number of blues as purples, but just by chance, when I was dumping them, and I remember as I was dumping thinking, wow, that's a lot of greens, I didn't mess with it. I just dumped until it was 32 grams, and then I put it in the bag. That's all I did. But anyway, maybe by chance, I got gypped with my blues, and I have too many lavenders. So I want to know, what would I expect if the original population, which is the whole bag or all the M&Ms in the world, if they were equally distributed? So divide that number by 5, or multiply by 20%, whichever you want to do. And that's what we would expect. So for me, I would expect 7.2. 36 divided by 5 is 7.2. By the way, whenever you divide by 5, there's a quick, easy trick you can do. Multiply by 2 and then move the decimal place. So 36 times 2 is 72. Move the decimal place. Anyway, so that's dividing by 5. It's because we have a base 10 fingers on our hands. Okay, now things get tricky. So everyone probably has different numbers here, but your expected numbers are all the same. So hopefully everyone's got the same, or not the same, has numbers that make sense. If anyone's confused though, stop me now. Yeah, by the way, this is all by hand. We could use Excel. In fact, if we have time, I'll show you how to do this in Excel, but it's not worth it, at least not for this. It's so easy. Okay, next, with my chart, you can probably just read down. So if you're confused though, I'll explain. The next one, we're going to do the observed minus the expected. So that's what this is. I think on the previous slide, I had expected minus observed. It doesn't matter. I just have it observed minus expected because it's easier to think of 3 minus, well, maybe it's not. That's going to be negative 4.2. This is going to be 0.8. This will be negative, so you can do it on a calculator if you need to, negative 6.2, and so on. I'll give you a minute. You can compute your own numbers. Okay, let's see, just a minute. I am not happy with my numbers. And something's off. Oh, this one. Sorry, I knew something was wrong. Someone would have figured this out. Yeah, it's the green. Sorry, this is why it may be safer to do it on the calculator. 1.2. Okay, the reason why I knew something was wrong is because if you were to add all of these numbers together now, you actually get 0. So you could try it if you want. I actually just did it and I was like, wait, not working. But if you take these, some of them are negative, some of them are positive, but if you add these together, they actually cancel each other out and you get 0. Everyone will get 0 if you've done it correctly. You don't have to. I'm just saying that that's what happens. So that's the reason, just like when we're doing other calculations in statistics, that's the reason, or one of the reasons why we're going to square these numbers. So now probably you're going to have to whip out your calculator. I will. I will humble myself and use a calculator. So I'm just going to take each of these, -4.2, and square that. And when you square a negative number, it becomes positive. So give me a minute here to do these calculations. Some of these I can do in my head. Okay, so I'll pause for a minute, make sure that we're all okay with this. So I know we're all going to have different numbers, which is a little irritating that we don't have an example where we all have the same numbers. I'll get one though, but it's just so much fun to have them in. Oh, by the way, if you're dying to eat, you can, as long as you've got your numbers, you can just shove them all in your mouth if you need to. Let's see. Oh. I didn't realize there would be so many. I should have known. I think I got a bigger bag than, yeah, don't do that. I'm going to be, yeah, I think I'm going to be bouncing off the walls here in a minute, and then I'll have the sugar crash after class. Okay. Okay. Sorry about that. Okay. Final thing. We're almost there. Whoops. Super exciting. Okay, so the final thing. Yeah, that was a big mistake. I'm not feeling so good. Okay, so now what you got to do is you do the division. So you take this and you're like, okay, how big is this? It's a big number, or this, 116, huge number. But you're comparing this to what you expect. So if you expected 116, then this number's not that big. So, but actually this is quite big. Most of you hopefully don't have these big numbers, but maybe you do. So I'm going to divide each of these by the expected. And in this case, every one of them gets divided by 7.2. However, you might, like in a different problem, you might have different numbers for your expected frequencies. But for us, it's all 7.2s. So let's see if I can do this. So you can kind of see that Excel would help a little bit, but it's not entirely necessary. Okay, we're almost there. So the final step is the total. You'll notice that at the bottom on yours, it says Chi-Squared down here. And so this total is just the total of those 5 numbers. You add them up and put them there. So, oops, let's see, turn this back on. So I'm just going to add mine up. So you're going to do the same thing. And I'll tell you right now that my number is probably one of the larger numbers. I don't know. Does anyone have a number bigger than 24? Wow, okay. Or maybe you don't know what your number is. Mine's 24.28, which is pretty big in all honesty. So now we got to deal with the table. See, do I have the table? I sure hope so. Where is my table? Is this the table? That doesn't go back far enough. I didn't update my stuff with a good table. I'll have to go dig the table out. Okay, that's okay. This will give us a chance. We have to look at Knewton anyway. So let's see, chi-squared, goodness of fit, whatever. Save it up here. Give me a sec. Let me just pull this up. I'll put it, preview. Okay, so here, we'll come back to the M&Ms in just a minute. Let's see, can I see this too? Okay, so you can see, basically, you're going to be doing something similar. It says do the, do this calculation, which you can easily do. You do the subtraction, expected and observed, and so forth. I'm just going to cheat because I can. Submit. I just want to get to the table. Okay, so anyway, you're going to do that. Okay, oh, come on. I want to get to the table. Okay, great. Yeah, easy stuff. Okay, instructor cheat. You can deal with this. Continue. Come on, people. Okay, if this doesn't have a table next, I'm just going to have to go do something else. Oh, finally a table. Good. Okay, so then you get a table that looks like this. So in our case, we need to know how many degrees of freedom. We also need to know an alpha level, but for the sake of simplicity, let's just use 5%. So 5%, that's this column. Now, how many degrees of freedom? How do you do degrees of freedom? Well, here's how you do degrees of freedom, is let's go back to our table here. Here we go. And you'll notice that I have 36 M&Ms, 36 M&Ms. If I were to go to a new table and then fill in 36 M&Ms, how many places I could put those M&Ms? Let's just say that I have, I'm in the dark, and I can't see, but I can feel my M&Ms, and I'm just like, I don't know how many reds I have or pink, but I could guess, couldn't I? And I could just say, oh, I've got 5 pink. So if you were going to fill in this table without counting, but you knew that you had to have 36, you could put maybe 5 here. You have complete freedom. Well, it's got to be less than 36. You could put 10 here, any number you'd like, as long as it's small enough. You could put 2 here, 5. You have freedom up until now. So I have freedom to pick whatever numbers I want for those 4. But the last one, if I want the total to be 36, there's only one number that's going to work there, isn't there? And that number is 14. How did I get 14? Well, I want the total to be 36, and I've already distributed 22, so I better put 14 there. So all that is to say that degrees of freedom for this particular thing, degrees of freedom is the number of categories minus 1. It's always 1 less than the number of categories. So here we have 5 categories, and if I'm just, if I gave you the task of filling in this chart, let's say I did this, and I said, you've got 36 M&Ms, you can distribute them however you'd like, then you could choose to put 8 here, 7, 6, 9, but when you got to the green ones, if you went in order like that, you would not be able to choose your number because the number would be chosen for you by the fact that there are 36 total. So categories minus 1 is degrees of freedom. Let's go back to the one that we're doing. In this case, degrees of freedom are going to be 4. Okay, so as I do this particular hypothesis test, I compute my degrees of freedom, categories minus 1, so 4. And then I go to this table. Where'd my table go? Just a sec. It's over here. And remember, we're going to just stick with 5% for, so go down to 4 degrees of freedom. The critical value, that's what we call these, The critical value is 9.48. I'm just going to write that down. Hold on. Whoops, not there. Just a minute. I'll show you what I'm writing after I get done. 9.488. Is that what it is? 9.488. So you want to jot that down somewhere. I didn't leave you a lot of room. I certainly don't have a lot of room, so I put it way up here in the top left corner. But that's what you're comparing this to. I could have written that down at the front end if I wanted to, because I knew that there were 5 categories, 4 degrees of freedom. I could compute that at the beginning. So I'm comparing that to this. So the question is mine more extreme or less extreme than that number? And it's certainly way more extreme. And so my conclusion is that there is evidence to suggest that Easter M&Ms are not produced in equal, percentages, that they're not all the same, at least, with the plane. So that's what I got. Now I'm guessing that some of you, because yours probably weren't, did anyone here have a critical or the chi-squared number that's less than that? Oh, a lot of you. Were you peanut? Any plane people? You're plane and you were less than this? Okay, so I was just curious. In fact, I'm so curious that I'm going to ask you to share your results with me in just a minute. Yeah, if your number when you get down here is less than that, then your conclusion is that there is not enough evidence to suggest that the color distribution is not just 20% across the board. So the peanut people, I'm not as impressed with your being, under this number, because you have such a small sample, don't you? You had maybe 10 or 12 M&Ms, and so there's just not enough data there. And so in order to get more data, I wanted to get a little bit more data. So I'm asking you to share your results with me. And so this is a pretty simple thing. Here, let me just freeze this for a minute, and you can do this. Oh, if you don't have your phone, oh come on, everyone has. Well, if you don't want to scan this, just a minute. I'll get the web address. You can do it. Let's see. Can I scan it from here? Oh, come on. There. Come on, buddy. Oh, there we go. There it is. So this just takes you to a Google form where I can keep track of all of the M&Ms. So let me show you what this gets to, and I get. Oh, that's too much. I was going to share the link. Okay, how about this? If you don't want to scan this for whatever reason, I don't know why, you can. I'll put a link. I'll put a link on our Moodle page in just a bit. For now, though, you're just going to have to hang on to your paper. You can do this later. My mother-in-law is scared of scanning QR codes. She says, "Oh, if I scan it, then they're going to know who I am." I mean, it is true that if someone mails you a QR code and you scan it, it might be like personalized in terms of like they'll know that you scanned it, whatever. But yeah, so she doesn't scan QR codes. She's 80 though, so. But anyway, let me show you what. Here's what you're going to see is this, and then we can fill in. So here, gender is optional. If you don't want to tell me, I'm just curious, like if you picked plain or peanut, just what the. So I'm gonna tell you. I'm gonna tell myself my gender, and I forget how many. Oh, I hope there's enough there. Did anyone run out? Does anyone have more than 20 of a particular color? Because I had 18, didn't I? Of the just a minute. How many did I have? Oh, come on. Let's see. Go back here. Yeah, I had 18 lavender. That seems really unusual. That's half. That's half of my M&Ms were lavender. Oh, they're in my body already. I was going to look at the bag. Yeah, that doesn't seem to be common. This looks more, I mean, there's only one blue, though. There's only one blue. So, okay, so let's see. 3, 8, 1, 18, and 6. Let me type these in. Let's see. So we have 3, 8. Isn't this clever? 1, 18 for the lavender. And then, where was it? 6. Okay, so I guess I probably could have computed that myself by figuring out how many would I need to make it 36. There it is. So submit. And then, so the reason why I want to do this is because next time I will present the results in full so that we can take all those peanut M&M stuff together and see if together we have a sample that's big enough to reject the null hypothesis. Because did any peanut people reject their null hypothesis, have bigger than 9? Wow, no peanut people could reject the null hypothesis. Well, that's typical, actually. It's not that surprising. So very nice. Okay, so that's that. So anyway, getting back to this, when you're doing the chi-squared distribution goodness of fit test, there are some. Now, I think that all of the stuff on Newton, I think they're all like the one we just did, where we're just comparing with an even distribution. But we could also compare with a distribution like this. You see, the distribution that we're interested in might be, like something that is not an equal distribution, which is totally fine. Let's see, do we want to do this? Just a minute. How to make, oh yeah, let's do this. Okay, let's do this one first, and then we'll go back. So some of you may be familiar with this little nursery rhyme or whatever it is. Monday's child is full of faith, fair of face. Tuesday's child is full of grace. Wednesday's child is full of woe. Thursday's child has far to go. Friday's child is loving and giving. Saturday's child has to work for a living. And the child that's born on the Sabbath day is bonny and blithe and good and gay. I think that in modern days they've changed this, but anyway, I'm a Thursday's child, by the way. This is based on when you're born. Just a silly little nursery rhyme that I remember being read to as a child. But it begs the question: are children born? Is it equally distributed? Well, you know that I have the data, don't you? Because you've been using that data for these projects. So here's the data. There's the babies. This is the entire data set out of 39 million babies. You have this distribution of babies being born on these 5 or 7 days. So are they equally distributed? I think you know the answer, don't you? But let's double check using the chi-squared distribution. So I won't make you do this calculation because it's kind of complicated. Well, it's just only the numbers are big. It's not that complicated, but I did it for you. First off, given that there's about 40 million babies that were born in the sample that I used, divide that by 7 and you get about 56 or 5.6 million for each day of the week. And then we can just do the same thing that we just did with our M&Ms. Here's the work that, I didn't show my work, but you can do this. You can imagine subtracting, squaring, dividing by this, adding them up. And here's my chi-squared number. What is that? 969,000. That's huge. I mean, I'm definitely rejecting the null hypothesis, but let's go through the motions. So the next step, of course, is to find on here the correct chi-squared value. And let's use here, how about this? We will use alpha is equal to 0.01 just for fun. And see if you can find the correct critical value on that chart with alpha is equal to 0.01. And remember that there are 7 days of the week. 7 days of the week. So take a minute, pick it out of the bunch there, zoom in on it, and I need to wash down all that sugar. That was a mistake. I used to do that, and I think I've just gotten too old. I can feel the crash already happening. But anyway, so here's the 0.01, and of course there, oh, no, that's not it, is it? I almost messed up. Yeah, I'll blame it on the M&Ms. It's this one, isn't it? Because you have to say 7 days of the week, so the number of categories minus 1 is the degrees of freedom, 6 degrees of freedom. So we're talking about this as the critical value. Clearly, this is way bigger than the critical value, but I just wanted to point out that that's the way it is. Now, let's see, we have 10 minutes left. So let's do one more thing, just to show you that we can do this with Excel. Let me go back to, let's see, where is it? Here, is this it? Yeah, let's see. So just a sec. Let's cheat on this one as well. I need a fresh one that we can start. just to show you what's going to happen. Okay, whatever, instructor cheat. Oh, come on. Click the wrong thing. Hold on a sec. Oh, way to go. I don't want to be good. I want to be bad. Here, let's see. I should have gotten it wrong so that it would force me to do it again. Oh, it's correct. Okay, I guess I have to start fresh. Just a minute. Let's close this. Take a sec. It's like a bumbling grandparent or something. I guess that's what I am. Okay, just a sec. Where is it? It's goodness of fit. Preview. Okay, pull this over. Can we see it? We can. Okay, so here's the sort of thing that we're doing. So let's see. Oh yeah, this is very similar. Babies being born. So we would expect babies to be born approximately the same in each season of the year: spring, summer, fall, and winter. Here's some observed frequencies that this is probably made up. I don't think that, well, I have the data. I could look into this. Be interesting. But I don't think that it's quite this different. But anyway, I mean, technically, babies being born in summer means that they are conceived in the fall, right? So I don't know, when would you expect babies to be conceived? But anyway, getting back to the problem at hand, we want to know, we're going to do this goodness of fit test. And so we have to select the null and alternative hypothesis. So let's deal with null hypothesis first. Seasonal birth rates have a uniform distribution. That means all the same. So that is going to be the null hypothesis there. The alternative hypothesis, I think you can probably guess, is the opposite. They do not have uniform. So when you see this phrase, uniform distribution in Newton, it just means all the same, 20%, 20%, 20%, or in this case, 25% for each one. So there's the first thing that I wanted to make sure that you see. Hopefully we'll have time to do the Excel. Great, good, good. Okay, moving on. Do we have the data? Yes, we have the data. Okay, the test statistics. So here's how I would do this if I wanted to do this using Excel. So just to show you, just a sec, I'm pulling up an Excel thing here. Okay, let me put it over here so you can see it and make it huge. Okay, so I have just copied and pasted my numbers in here. That's ugly. Hold on a sec. Can I make this? Whatever. You don't need to see that now. So there's the numbers. So here's what I would do is I'm going to take this little chart that I gave you. Okay. And I'm just going to reproduce it. Yeah, the caffeine, the M&Ms, the sugar. And I'll do it like this. I'll just do this equals expected minus observed. So that's easy enough. And once you have that, you can go all the way across here to the right. Great. So that's the expected minus observed. I could even write this like this, E minus O. And then this thing is going to be E minus O squared. So this will equal this thing squared. And I think you can, now if you need to, you can always watch the video again, and I'll get a few more views this time. And then this is going to be E minus O squared over E. Sorry, I had to think for a minute. So that's going to equal, whoops, that's going to equal this number divided by the expected number. And then do this all the way across. And then you just need to add these up. So then you can maybe over here or down here, or I'll do it down here, chi square. The actual number is equal to the sum of, let's highlight all of this. There it is. So it is possible to do this in Excel. There's my actual chi-squared number, 22.35. Let's see if they like me. I'd be sad if I don't get this right. Let's see, how many digits? 3. 3 decimal places. That means I have to round this to a 1, I think. We're going to find out. Submit. Oh, great work. I'm doing great. Look at that. It even did it there. But you can kind of see that you could do this by hand, but it's a little laborious. It was pretty quick using Excel. Let's finish this one up just so that we're happy, and then we'll call it a day, and you can come complain about the test. Oh, I forgot to mention that. Of course, as always, I'm happy to hear your cries for mercy about your particular exam if you think that I wronged you in my grading. please do stick around. Okay, getting back to this, it says blah, blah, blah. We have a 1% significance level. That refers to alpha. So here is 3 degrees of freedom because there are 4 categories, 3 degrees of freedom. So 11.345 is the critical value. And of course, when you get to the quiz next time and the exam, you're not going to be able to select like you are here. So be aware that your conclusion is going to be the same as it's been all along. Since my chi-squared value is bigger than the critical value in this case, I'm going to reject the null hypothesis, and there is sufficient evidence to conclude that seasonal births do not have a uniform distribution. So you can make sure that you don't just click and not read. Read it over so that you can internalize this wording. If you had written, some of you, if you had written something like this, I know it's not the same type of problem, but if you had written what Newton had on your test, I would have been so happy. So make sure you at least read this over so that you say, okay, that's the way I'm supposed to write it. Yes, there is evidence to suggest or conclude or whatever that seasonal birth rates do not have the uniform distribution. Okay, it sounds a little weird, but it's understandable. Look at me, I got it right. I am so happy. So, yeah, way to go. Why don't you stick around if you want to chat about your test? Otherwise, we'll see you on Friday. And if you don't want to eat your M&Ms, you can give them to a friend. So